Number 27. Suppose that X has a probability distribution given below. What is the variance of X? Problem 27, exam 3 of 8. So here we're asked to find the variance of X. The variance of X, the formula is a sort of a shortcut formula, is the sum of the xi squareds times the probability of each xi minus the sum of each xi times the probability of that xi quantity squared. Can be rewritten like this. So first of all, I want to find the expected value of X. So they give us certain values and probabilities that each X can take on, and these are it. Now this last one they just call P, but you know that the probabilities have to add to 1. So 0.2, 0.3 is 0.5, 0.4, total will be 0.9. So the only thing left over is 0.1. So I just went ahead and stuck it in there. And that solves to 4. Now for this piece, the expected value of X squared, you just square each value times its respective probabilities. You get 21. So the variance of X is 21 minus 16, which is 5. Number 28. Let Y have a chi-square distribution with 32 degrees of freedom so that its variance is 64. If the probability that Y is greater than C is equal to 0.0668, then the constant C is approximately equal to. Now, number 28, they give us the probability that Y is greater than C is equal to 0.0668. So now, I'm going to solve this two different ways. One is I'm going to look in the back of the book. So in the back of the book, the closest thing we have to 0.0668 is 0.05 and 0.1. So the C values to get those is here. Well, we know it has to be something between those two values, and the only answer that's between those two values is 44, so it must be 44. Okay, so that's one solution. But I really think that this problem is wanting you to use the central limit theorem to solve this. So here, if we let X be chi-squared 1, then we know that the sum of chi-squares is chi-squared, and we're summing 32 of them because it's 32 degrees of freedom. So if we let Y equal be this sum, that's chi-squared 32, which has an expected value of 32 and a variance of 2 times 32. Well, the central limit theorem says that when you're adding up a bunch of variables, and of course the second moment has to be finite, or the variance has to be finite, then it follows a normal distribution. So if we let, we're given that Y is greater than C. So if we subtract the mean and divide by the standard deviation to both sides, then we get a Z statistic, and we know the problem says that it equals this. So then when you're looking in the back of the book for a standard normal, it implies that this value, or the Z that's greater, has to be 1.5. So 1.5 equals this quantity. You solve for C, which is 44. Number 29. If the cumulative distribution function of a random variable X is given by f of X equal to 0 when X is less than 0, 1 minus X e to the minus X when X is greater than or equal to 0, then what is the moment generating function? In problem 29, we're asked to find the moment generating function. And we're given the cumulative distribution function of this right here. And notice there's a big jump at 0, and then of course it limits to 1. And you can find the density, probability density function by taking the the derivative of it, and you come up with this. And this seemed a little odd, I think. So what I did was I integrate this area to see what it equals, because it, you know, in a probability density function should have area 1. So when you integrate it, it is equal to a half, and so we're missing something. Well, then you can show that there's some value when x equals 0. So when x equals 0, there's a probability of a half, and then when you're strictly greater than 0, then you're using this density. So to find the expected value of t to the x, this is the definition of a moment generating function, you have to take it over each region. So this one, so when x equals 0, you know, it's 1/2 e to the t, and then the value of where you are, which is 0, and then we're going to integrate from 0 to infinity of this, the expected value of tx, you know, times the density. And okay, I added a 1/2 here. I missed it earlier. So you integrate this. Well, this first one, anything to a 0 is 1, so you just get 1/2. And then when you integrate, you can combine the e's to e to the x, t to the 0. And then when you integrate it, you know, you end up with a dividing by t minus 1, e to the x, t minus 1. So when you plug in these values, you have to note that when you plug in infinity to x, that goes to infinity unless this is negative. So unless t minus 1 is negative. So we have to assume that's negative, and then this goes to 0 when you plug in infinity. So then when you plug in 0, you just get this piece here, because that's 1. So you get 1/2 minus 1/2 times 1 over t to the minus 1/2. And then that can be reduced or combined to this. And again, this is where t is less than 1. Number 30. Suppose that x and y are two independent, identically distributed random variables. Let z equal to a times x plus y. If the correlation of x and z is 1/3, then what is the value of a? So problem number 30, we're asked to find the value of a such that z equal to ax plus y, you know, such that the correlation of x and y is 1/3. So if we just look at the covariance, we have to find pieces of the correlation. So the covariance of x and z is, since that's a linear combination of x and y, you break it up. Well, they're independent, so that covariance is 0. So we're just left with this. So you bring out the a, and the covariance of x and x is the variance. Well, we're going to call that a times sigma x squared. So now if we look at just the variance of z, which is this linear combination, then it's the variance of the individuals. So it's the variance of this, but you have to take out a squared, and you get the variance of x squared plus the variance of y squared. Now, the correlation of x and z, which they said was 1/3, is defined to be this: the covariance of the variables divided by the standard deviation of each variable. Well, let's put in the symbols that we have. The covariance we have to be a times sigma x squared, and the variance of x is sigma x squared, and the variance of z we just found to be this. Well, this is a product, this times that, and so this is the square root of x sigma x squared. So this piece and this piece can be combined into this. It kind of reduces to that. So we have this. Well, that's equal to 1/3. So we're going to square this and square that, and we're down here. So we get 1/9 equal to this quantity. Well, we are going to multiply this side up here, multiply this over here, and then take it to the other side. And we get this. Now we're going to solve for a squared. So this piece we're going to subtract over. That's why we get the minus sigma y squared. We are going to, this is minus 9 a squared sigma x squared, and this is 1 sigma x squared. So that's minus 8 a squared sigma x squared. So then we divide by this piece here. And since x and y are two independent, identically distributed variables, the variance of y and the variance of x equal. So that cancels, leaving minus 1 over minus 8, which is 1/8. Then you have to take the square root of both sides and you get this piece here. Number 31. Let C of m comma a alpha be the 100 alphth percentile of a chi-square distribution with m degrees of freedom. Assume that x1 through xn are an independent random sample, each normal with mean mu and variance sigma squared. The usual symmetric confidence interval for sigma squared when mu is known and is constructed by first recognizing that the distribution of this quantity is chi-squared. What is the expected length of such a confidence interval with confidence 1 minus alpha? Now, number 31, we want to find the expected length of a confidence interval. So here's a note first of all. So if x is chi-squared, well, x is this quantity, which we know is chi-squared n. That means the expected value of x is n. Now, if we take the expected value of a constant times x, then you can bring the constant out, and that's the constant times expected value of x, which is just n. So we get this piece here. Now that's going to play a part in a second here. Notice that this quantity here, sigma squared times x, if you plug in the x for this, the sigma squareds cancel and you just get this top piece right there. Okay, so here's the definition, or the definition of a confidence interval. 1 minus alpha is equal to the probability that x is between these two values. Well, if we plug in x, which is this here, then we have to take the reciprocal, which then these inequalities change, and then multiply both sides times this denominator, which after you flip it's the denominator. So those go up and we get this quantity here. Well, the length of this interval is this minus this, which is this. So the length is equal to this quantity here. Well, now we want to find the expected value of the length. So here, this is a constant, so it goes out front. And this piece right here is this we found to be sigma squared n. So this constant goes out front, and the expected value of this quantity is n sigma squared. So that's the answer. Number 32. Let u and v be random variables with joint density function f of uv equal to 1/2 uv, where u is between 0 and v is between u and 2. What is the probability that u is less than or equal to 1/2 given that v is equal to 1? So number 32, we want to find the probability that u is less than 1/2 given that v is 1/2. So here we're given the joint density. We have to find the v, because that's where we're going to find this conditional distribution. So you integrate out u and you get v cubed over 4. So then you take the joint divided by the marginal, and you get this 2u over v squared. Now remember, u is between 0 and v. So the probability that u is less than 1/2 given v is equal to 1. So you plug in 1 to this equation, and then you're only left with 2u. And we want to be less than 1/2, so we're integrating from 0 to 1/2. Integrate, plug in the values, we get 1/4. Number 33. If the cumulative distribution function of x is given by 1 minus e to the minus x when x is greater than 0, then what is the cumulative distribution function of y, which equals to e to the x over 2? Now 33, we want to find the cumulative distribution function of y, which is by definition this, the probability of being less than or equal to little y. Well, capital Y is equal to e to the x divided by 2. And then if you take the natural log of both sides, you get x squared is less than or equal to log of y. Multiply the 2 up. Now, so when you have 2 times the log of something, remember that multiple out front can be rewritten as an exponent. So you get the probability x is less than or equal to this. Well, we know the cumulative distribution function of x, so we just plug in this value into the equation, which is here. Now this minus in front of here can be taken up to the 2, so it's a y to the log of y minus 2, but e and the log kind of cancel and you're left with this right here. Number 34. If a random sample of size n is drawn from a normal distribution with mean mu and variance 1, the null hypothesis mu equal to 5 is to be tested against the alternative hypothesis mu is equal to 6 at the significance level of alpha equal to 0.05. What is the smallest sample size such the test has power of at least 50%? So number 34, we want to find the power of the test. So we want to first find the rejection region. So the probability that x bar is greater than c is alpha, and this is under the null hypothesis. So then if we subtract the mean divided by the standard deviation, it's a z. And we want it to be 0.05. So this value needs to be 1.645 in order for this probability to be 0.05. So that implies that this quantity, which is this, equals here. You solve for c, you get c equal to this. Now we want the power to be greater than or equal to 0.5. So that means under the alternative hypothesis, we want x bar greater than c to be greater than 0.5. Well, this is a normal distribution. So you subtract the mean divided by the standard deviation and then you get a z. Well, to be greater than 0.5, then that implies this quantity here is 0. So then you set this equal to 0 and you solve and you get c is equal to 6. Well, if you put c back into here, here, which is 6, then you solve for that, you get this equation, multiply up, take the square each side, you get n is equal to 1.645 squared, which is 2.7, which is approximately 3.